Okay, so this is going to be a recap on everything that we did today for chemistry. Okay, so firstly, we're going to be taking a look at our periodic table and why it's so important and all that stuff. So, in my atom, okay, in my atom, I know in the center this is called a nucleus, and I have protons and neutrons inside there. Protons are positive, neutrons have no charge, okay, and then around it are going to be my electrons orbiting it, so they're going to be moving. Now, when I look at my periodic table, okay, so look here, you'll see I have two numbers. So let's look at beryllium here, for example. I have a number on the top and I have a number on the bottom. Now, the number on the top is called your atomic number. It tells me how many protons there are in this element and how many electrons there are. So in this element, beryllium, there's 4 protons and there's 4 electrons. Right. In this magnesium, there's 12 protons, 12 electrons. Your proton and electron number will always be the same. Then the number that's below your element is just the atomic mass. So it's just the weight of that element. Now, there's another number that's on these elements, and it's not shown in this periodic table, but in your exam it'll be there. So see, I have a number on the top and on the bottom. Then there should be a number here on the side. It's a decimal number. That's called your electronegativity number, right? Now that tells me how electronegative, so how negative that element is. And I'm going to use that to help me later on with certain calculations. So I established that this atomic number tells me how many electrons there are in that element. So there's two types of electrons that we get. Okay, so firstly, you'll see the atomic number is a number of protons and number of electrons that are there. Now, there's two types of electrons that we get. The first type is called core electrons, and then the second type is called valence electrons. Now, the core electrons, if I take a look at my atom, your core electrons are going to be the electrons that are closest to your nucleus here. And then the valence electrons are going to be the electrons that are further away from the nucleus, so in the outermost shell. So that's how I'll describe it. I'll say that the core electrons are electrons close to your nucleus, and the valence electrons are the electrons in your outermost shell of the atom. And it's these valence electrons here, the ones that are in your outermost shell of the atom, on the outside, they are the ones that are involved in chemical bonding. So they'll come out from this atom and bond to an electron from another atom, and it'll be valence electrons. So when we look at our periodic table and you see elements, I want you to think of them as atoms as well. So like this is a hydrogen element, I'll say it's a hydrogen atom. This is a beryllium element, it's a beryllium atom. Okay, and they're going to have their electrons, protons, and so on. Now, how do I judge? So I just understood what core electrons is and what valence electrons is. When I look at my periodic table, I will be able to tell you by just looking at any element. I can tell you how many valence electrons it'll have. So what is valence electrons? I told you it's the electrons in the outermost shell of that atom, and it's the electrons that will be taking part in bonding, basically. So, for example, this is how I want y'all to learn it. You count this number. So we're looking at columns here. Everything under column 1 will have a valence of 1. Everything under column 2 will have a valence of 2. You forget all of these columns in the bottom. Everything under column 3 will have, so see this says 13. Treat it as 3, 4, 5, 6, 7, 8. So everything in this column will have 3 valence electrons, 4 valence electrons, 5, 6, 7, and 8 valence electrons. Now, how do you show your valence electrons? You need to use Lewis dot diagrams. So, for example, if they told me to draw the Lewis structure for H, I'll go and look for H. I can see H is here under the first group. So what is its valence electron? It has a valence electron of 1. So then I'll go and you can use dots or you can use X's, whatever you prefer. That's how many valence electrons H has. Then chlorine, you can find it. There's a here in the 7th. So I know it's going to have 7 valence electrons. And now you need to draw that. So how would I draw it? See, there's 4 spaces here. So I can put 4 dots. But now chlorine has 7. So after I put my 4 dots, I must go and put dots in the places again until I reach my 7. So for example, 1, 2, 3, 4. Now I need to go again because there's 7. 5, 6, 7. Now, do we see that? I filled in these pairs. There can only be 2 electrons per space. And now what you notice is this electron is by itself, and so is this electron. So you can bond these two. So you connect it together. Let's represent H's electron with an X so you know where it goes. So if I bond these two together now, I'll have Cl, and then the electron from there bonded with this one's electron, HCl. Now that's how you show your Lewis dot diagram, and basically how you showed the bond taking place. Now I want you all to look very carefully here. See these bonds here that were originally on this atom. We call these lone pairs. It means 2 electrons that were paired together originally on that atom or element. Then look at this one. This is a bond pair because it's an electron from this atom and electron from the other atom bonding together. So these are your lone pairs and this is your bond pair. Okay, so that's how we show Lewis dot diagrams, and that's how you can tell your valence electrons. Now, remember we did valence electrons and core electrons. The atomic number tells us how many electrons there are in total. So let's see if we saw boron, for example. So I see that boron is here. How many electrons does it have? Look at your atomic number. It has 5 electrons. But how many are valence electrons? So how many in the outermost shell? There's 3. So how would I get the number of core electrons? I'll take the 5 minus 3, so I'm left with 2 core electrons. That's how you can work with core electrons. I doubt you'd ever be asked that question, but just so you'll know if we want general knowledge. Okay, now look at this last column here. How many valence electrons would this have? It would have 8 valence electrons. So let's draw that out. Let's take helium. So He. 1, 2, 3, 4, 5, 6, 7, 8. So I can see that all my 4 spaces are taken and it's all paired up. So it's all got lone pairs. So they're leaving me with actually nothing to bond in here. When all 4 spaces are taken up by the electrons like this, all 4 spaces are taken up by lone pairs, I call this a noble gas. Okay, so when it's a noble gas, or when it's at noble gas state, that means it's at its most stable state. So this is another term that's going to come into play. It's called valency. Now, valency is when I can pick any element from this table, and I should ask you what's the valency of it. So what is valency? Valency is how many electrons you have to add or take out from an element in order to make it reach this noble gas stage. So this is how I want y'all to remember it. See your first, second, third, and fourth column. All you need to know is those ones are going to gain electrons. How many are they going to gain? Everything under the first column will gain 1 electron. Anything under the second column, 2 electrons. Here, 3 electrons, and here, 4 electrons. Then as I go from 5, 6, 7, it's going to lose electrons. And the numbers you need to remember here is this one loses 3, this one loses 2, and this one loses 1 electron. And then obviously in your 18 group, you don't need to lose or gain because it's already at a noble gas stage. So if I randomly just point it as like, what's the valency of beryllium? You should see it's 2 and it's in the gaining part. So its valency is 2, right? It gains 2. Here the valency will be 3, it gains 3. Here the valency, all of these gain 4. Here the valency, they lose 3, lose 2, and lose 1. And here the valency will be 0 because it really doesn't need to add or gain anything to this column. Okay. Right, now I need you all to know the difference between intramolecular forces and intermolecular forces. So the intermolecular forces is going to be those dipole, all of those things, right? We're going to come to later on in the video. Intramolecular forces is going to be covalent, ionic, or metallic. Those are the 3 types of intramolecular forces. So firstly, what is intramolecular forces and what is intermolecular forces? So you know what a molecule is. For example, if I had HCl, that's one molecule, right? Then if I have H2O, that's another molecule. When I say intramolecular force, as I was saying, when we look at intramolecular forces, we look at into that molecule. So molecular forces are attractive forces, right? Intra is within this one molecule. So see, there's a hydrogen and there's a Cl. It's the bond or the force of attraction between this hydrogen and Cl. That's intra. It's within that molecule. When I say intermolecular forces, it's between two separate molecules. So see, this is one whole molecule, this is another whole molecule. This will be the intermolecular force. So one more time, intramolecular forces is the attractive forces within the elements of, between the elements within one molecule. Intermolecular forces is the attractive forces between two separate molecules. Okay, so the three intramolecular forces that we deal with is covalent, ionic, and metallic. Now, covalent is between a nonmetal and another nonmetal. Ionic is between a nonmetal and a metal. And then metallic, obviously in the name, it's a metal and a metal. Okay, so we're not going to be working much with metallic or ionic in this section, but it's good for you to know. Metallic we don't ever work with. It's always between covalent and ionic. Now, if you look at two components and you're like, okay, how will I be able to tell if it's covalent bonding that's going to happen or ionic? All you need to know is you will take, other than so for example, if you look at two elements on the periodic table, you can't just automatically know that it's non-metal and a non-metal, so then it's going to give you covalent. Because look at the periodic table, you're not going to know what's non-metals or metals or any of those things. So what I want you to do is, say here, I'm going to send you all the scale picture, obviously, but remember I told you about the third number. Like, see here, I got my atomic number on top, I got my weight on the bottom. And then I told you there's a third number on the side of your elements. That's called my electronegativity number. Now, for example, if you want to work out whether it's a covalent bond, ionic bond, or so on, let's say we use HCl. So they gave me HCl, and they want me to work out if it's a covalent bond, ionic bond, or whatever. So what you're going to do is, you're going to separate these into its components like that. I see a hydrogen, I see a Cl. So what you'll do is, you'll go on your periodic table, you'll look for Cl. There's it here. You look for its electronegativity. Now I told y'all, it's not on this diagram, but it's on the periodic table that I sent on the group. So your electronegativity number will be here. I think, let's just say it's 3.5, right? Then you look at your hydrogen. Hydrogen's like 2.1. Then how are you going to know if it's covalent or not? You will work out the delta En. What is En? It's your electronegativity. What is delta? It's our change in electronegativity. So all you'll do in this case is, the two elements that you're comparing within that one molecule, you'll take the bigger electronegativity number minus the smaller electronegativity number, and you'll get a value. That's how you get your delta En. So here, remember we're dealing with Cl, so you'll take whatever number, whatever decimal is there on the side, minus your H, whatever decimal is here on the side, and you'll get your delta En. Let's say you got an answer of 1.4. Now, how will this determine whether it's a covalent or ionic or so on? Now, this is what I want y'all to learn. So look at this now. This is a range that you have to know. So remember, I told you, if you want to work out what intramolecular force is between the molecule, you will go and work out its delta En. So its change in electronegativity, where you take the electronegativity of the bigger one minus the electronegativity of the smaller one. Where do you get your electronegativity from? I told you it'll be on the side of your elements. So after you do that, you get an answer. We got an answer of 1.4. Now go and look at it in your scale. If your electronegativity change is less than or equal to 2.1, it's regarded as a covalent bond. If your electronegativity is greater than 2.1, then it's an ionic bond. Don't worry about metallic because that never ever comes out, right? So if we look at our case, I see I got 1.4. So I know it's going to fall less than 2.1. So HCl will have a covalent bond. So that's how you work out the intramolecular force, whether it's covalent, ionic, or metallic. Okay, next, how to establish whether a molecule is polar or non-polar. So let's say we're given HCl. First step, you need to go and check. Okay, first draw your Lewis dot, right, of how these two bonded together. So I know my hydrogen originally had 1 and my chlorine had 7. This is according to my valence structure now. And then obviously these two bonded together. So this is my final answer that I would have gotten for my Lewis dot. Okay, now with this here, how am I going to establish whether this molecule is polar or non-polar? First step you do, you go to your periodic table and you check your electronegativity values for each one of these. So we'll go, again, this periodic table doesn't have it, so you must check the one in the group chat. So we have to look at CLs, so it should be on the side here somewhere, and let's just say it's 3.5. Then we'll have to go and check H's, and it'll be on the side here, so let's say it's 1.2 or 2.1. Now, from those two, what are we checking for? You're going to see which one has the higher electronegativity. So between the Cl and the H, my Cl definitely has a higher negativity. So I know that the Cl is going to have a greater negativity. And because this has a greater negativity, what's going to happen is these electrons are going to pull towards this way. So I'll draw my arrow going towards that way. And what's happening is as the electrons are coming more on this side becomes, let me just rub off this top part so you don't get confused. Right, as I was saying, as these electrons are pulling towards the one that's more electronegative, this side becomes partially negative. And if the electrons are leaving the H, then this side will become partially positive. And now that's what polar means. It's when you have two poles, a north pole and a south pole, for example. Here we got a positive pole and a negative pole. So then this whole molecule will be deemed polar because it formed two poles. Now another way you can work this out, which is generally the way that I want you to, you saw that the electrons shifted to the more electronegative one. So that's how you draw your arrow, going from the smaller electronegative to the bigger electronegative. And because there's one arrow here, you'll say it's unbalanced, and I'll show you what that means just now. And it's polar. So when there's one arrow by itself, it's automatically polar, right? What is this arrow representing? It's showing your shift of electrons from the small electronegative to the big electronegative, right? Now, let's look at another example and then I'll show you. But before I do that, when I say unbalanced, I want you to think of polar. When I say balanced, I want you to think of non-polar. Now, you know in your vectors where arrows of the same size, if they act in the opposite directions but the same size, they cancel each other off. Same thing goes for here. They're acting in opposite direction but the same side, so they cancel each other off. Remember, they must be on the same plane. Like a vertical will cancel off with a vertical and a horizontal will cancel off with a horizontal, right? No other way. When they all cancel off like this and there's no arrows left, that's called balanced, which is non-polar. But if I cancel and some are left, or if I can't cancel at all, then we say it's unbalanced and therefore it's polar. So in this instance, there was nothing to cancel off with this arrow. So it's unbalanced, so it's polar. Let's take a look at a non-polar example so you can see what I'm talking about. So let's say I had CH4. So first, bond it together. I know C is here, its valence is 4, and I know the hydrogens each have 1. So there's H, 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 and H bonding like that. Now, what's our step to draw arrows? We see which ones So we need to look at each one individually with the C because they each bond to the C. So I'll look at hydrogen has electronegativity of 2.1, for example, and carbon's electronegativity is higher than that. Remember, you must go check on your periodic table. So what happens is this H is going to, because it's got a lower negativity, it goes towards the carbon with a high negativity. This H goes toward the carbon in a high negativity. This H goes toward the carbon this side, and this H goes towards the carbon that side. Now, can we cancel here? Yes, we can. This and this one can cancel because they're going in opposite direction, but they're both vertical. And this one can cancel because they're going in opposite direction, but they're vertical. But they're horizontal. Now, if everything canceled off, we call this balanced. And if it's balanced, it's nonpolar. If it's unbalanced, it's polar. So I'm going to do more examples with you so you guys get like the hang of it. Okay, let's do CO2. So remember, I'm checking if it's nonpolar or polar. So first things first, you need to do your Lewis dot. So we got C, its valence is 4 electrons. Then I have an O and another O here. O's is 6 valence electrons. Okay, so now I can see what's going to bond with what. That will bond there, that will bond there, and then this one will bond there, and this one will bond there. So I can see how that's going. So if you want, you could put these as X's, so you don't get confused from your oxygens. Right, so it'll be like this, your final product. 1X, 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 O, and O. Okay, and then basically you have your 2 here and 2 here, and then 2 here and 2 here. Okay, now this looks very complicated, but just bear with the fact that this O bonded to the C, this O bonded to C perfectly. Right, now how am I going to know if it's polar or non-polar? Well, you go and check. This O bonded to the C, so you check the electronegativities between the two. So it turns out that the electronegativity on oxygen is less than the electronegativity on carbon. So this one is the more electronegative, so it's going to go this way. Same thing's going to happen for this oxygen and the carbon. It's going to go this way. So if it's going those two ways, what's going to happen? They're going to cancel off, and therefore it's balanced, which means it's non-polar. Okay, then let's look at NH3. So I have my N. N is 5. So I have 1, 2, 3, 4, 5. And now my H's, I know one's going to bond here, one's going to bond here, and another's going to bond here. So I got my shape. Now, let's take a look. Hydrogen has a smaller electronegativity value than nitrogen. So obviously, it's going to go this way. This hydrogen will bond that way, and this hydrogen will bond that way. Now, what can I see happening here? I can see these two will cancel off, but I'm left with one. So that means this is unbalanced because not everything cancels. So if it's unbalanced, then it's polar. Okay, and that's how you determine whether it's polar or non-polar.